Good afternoon, Year 10, and welcome back to Mr. Hunter's GCSE revision. As requested on the poll I sent out, the highest scoring category for which topic you would like to do next was atomic structure and radioactivity. So we're going to do some, we're going to just go through some questions together on this video. You'll have the textbook on Caboodle, some of you have physical textbooks, and some of you have the physical revision guides, and obviously all of the notes we went through in lesson. So I'm not going to go through more notes. That's possibly a waste of everybody's time. Instead, I'm going to go through some just some exam questions. And so if you want to, you can pause the video, attempt these questions yourself, and then unpause it for the solutions. So feel free to pause the video now. And here are the next set of questions for pausing if you need to. I'm just going to go through the answers. For the quick ones, I'll write straight on the question itself, but for the longer answers, I'll write underneath. And so just pause it when you need to. So question 1 says, calculate how many protons and how many neutrons are in a nucleus of each of the following isotopes. So this number down the bottom, the 6, that would be the number of protons. And so 6 protons, and then this is the mass number, and therefore 14 minus 6. Oops, I've jumped ahead there. Equals 8. 8 neutrons. Let's look at thorium. Thorium, we have protons equals 90, and then 288 is the mass number, so 288 minus 90 will give us the number of neutrons. Alright, just getting my calculator out, as I'm lazy and don't want to do that in my head. 3138, that's fine. So carbon 14 emits a beta particle. Remember, a beta particle is just an electron and becomes an isotope of nitrogen. Write down how many protons and how many neutrons are in this isotope of nitrogen. So we have to first think about the reaction. So carbon 14 turns into nitrogen plus a beta minus particle. You can write the 1, 0 instead on the left hand side if you like. You can write this instead if you like, or you can just go straight for beta minus. So a proton has turned into a neutron. A neutron has turned into a proton. So the proton number has gone up by 1, and the mass number will stay the same because there is no protons and neutrons leaving the nucleus. So how many protons and how many neutrons are in the nitrogen isotope? Well, the number of protons is 7, and the number of neutrons is also 7. 14 minus 7 is 7. Write the symbol for this isotope. We've got that here, nitrogen 14. So part C says thorium 228 emits an alpha particle. Remember, alpha particle are a helium nucleus, and becomes an isotope of radium. So let's write out this equation. Let's just go straight for it. It makes the questions easier. Radium, we don't know the numbers yet, the atomic number or the mass number yet, but we can work that out. And alpha, 42. How many protons and how many neutrons are in this isotope of radium? So the alpha particle is a helium nucleus, 2 protons and 2 neutrons. It's emitted 2 protons, so the proton number goes down by 2. The mass number, 2 protons and 2 neutrons, goes down by 4 then. And so clearly the number of protons was 88, and the number of neutrons is 224 minus 88. Let's just work that out. 136. Write the symbol for this isotope. Well, we've already done that, but let's write it out again. Radium 224. Copy and complete the following table about the properties of alpha, beta, gamma. So the identity of alpha is a helium nucleus. Gamma is a photon or high energy photon. It's basically light. It is light. Gamma rays are stopped by thick lead. Beta particles are stopped by thin aluminium. And alpha particles are stopped by paper or skin. Alpha particles can't penetrate the skin. Range in air, just a few centimeters. Let's make this a bit smaller actually. About 1 meter for beta, and the range of a photon of light is technically infinite. Or until it's absorbed. So what is it? Range in air. Yeah, pretty much it will go forever in air. Relative ionization, weak ionization, long range. Beta particles is sort of moderate ionization, a medium range. Moderate. And then alpha particle is highly ionizing, so strong ionizing. But it can't pass through the skin. But if you ingest it, then you are in serious trouble. And indeed is a favoured way of assassination by spies. Fun fact. So 3 is the following measurements were made of the count rate of a radioactive source. So the time in hours is going up in half-an-hour chunks. The count rate due to the source in counts per minute is coming down steadily. Plot a graph of the count rate on the vertical axis against time. Use your graph to find the half-life. So let's do this nice and quick. And so my graph will be rough. You might have graph paper in the exam. You'll have proper graph paper. Is the count rate in becquerels? Per minute. Count rate due to the source in counts per minute. Fine. And the time in hours. So we've got 0 to 2.5. Okay. Half, 1, 1.5, 2, 2.5. Fine. And then 150 roughly to 500. So we could go 150, 2, 250, 3, 354, 450, 5, 550. And let's go for some plots. So 0 is at 510. Half is at 414. Three, 3, 7. This is very approximate. 2, 7, 6. 2, 2, 7. And 188. Okay, so very, very approximate there. And let's draw in our line of best fit. It is decaying, clearly decaying. Let's draw it in. There we are. All right, that's good enough. So use your graph to find the half-life of the source. Let's do it. So the half-life is the time it takes for the count rate to halve. So we're going from 510 to then 265. So let's find out where 265 is roughly. Oh, it's roughly on this line. Let's just go for that. Nice and simple. 1.5 hours. All right. Good, we're done. 4. In a radioactive carbon dating experiment, the ancient wood, a sample of wood, had an activity of 40 becquerels. The same mass of living wood had an activity of 320 becquerels. State what is meant by the activity of a radioactive source. So the activity is the number of decays per second. So it's the number of radiation counts per second as measured by a Geiger-Müller tube. So I'll put decays per second as measured by Geiger-Müller tube. Calculate how many half-lives the activity took to decrease from 320 to 40. So we've gone from 320 to 160. Yeah. Then to 80, then to 40. So we've gone for 1 half-life, 2 half-life, 3 half-lives. So the answer is 3 T-halves. 3 half-lives. The half-life of the radioactive carbon in the wood is 5,600 years. Calculate the age of the sample. Well, the age will be 3 times 5,600. 56 times 3 gives us 168,000 years. So, question 5 says, in an investigation to find out what type of radiation was emitted from a given source, the following measurements were made with a Geiger counter. So we've got source at 20 millimeters from tube, average count rate in counts per minute. So we've either got the no source is present, no absorber is present, we've got a sheet of metal foil, or some thick aluminium plate. So part A says what caused the count rate when no source was present. So a Geiger counter will pick up some radiation even when you don't have any radioactive sources present, and that's because the count rate is the background rate. And where does the radiation from the background come from? It's just a base rate in the air. It comes from radioactive radon in air, some building materials as well. And so there is most of the background rate is actually from small amounts of radioactive radon in the air. So write the count rate from the source with no absorbers present. So the count rate from the source is this minus the background rate. So the true rate from the source will be the total rate minus how much the number of counts per minute from the background. And so we've got 385 minus 30 plus 1, so we're at 3 5 6. So 356. And then write what type of radiation was emitted by the source. Explain how you arrived at that answer. And so if we put some metal foil in between the source and the in between S and T, so in between the source, then the count rate remains the same. So we know that it can't be alpha, because alpha's not going to get through any metal foil. This says it does get through metal foil, but it doesn't get through thick aluminium. So I would argue that this source is either beta or gamma, and so we know, and it's 4 marks, so we can break this down. So we know. Actually, let's write this out properly. What question is this? 5C. So we know I'll put after metal foil, count rate did not change. After thick aluminium, count rate reduced to approx background rate. And so if source was gamma, count rate would be unaffected by thick aluminium. If source was alpha, then count rate would have reduced to the background rate after thin metal, because alpha can't get through that. Therefore, source is beta radiation. And so let's look at these points. We've got how many marks we've gone. 1, 2, 3, 4 arrives at this conclusion. All right. So question 6 says, figure 1 shows the path of 2 alpha particles labelled A and B. They are deflected by the nucleus of an atom. Explain why they are deflected by the nucleus. Because alpha is positive charge, nucleus is positive charge. I'll just put nucleus is positive as well. We all know that it's charged. Therefore, like charges repel. Explain why B is deflected less than A. Well, we just need to look at the paths. If we had, let's say that we had C, and C coincided perfectly with the center of the nucleus, then the particle would just come straight back. And so it's because A is closer to the center line of the nucleus, technically, and therefore it approaches the nucleus closer. And so explain why B is deflected less than A. We'll put B is further away from a direct collision. Explain why most alpha particles directed at thin metal foil pass straight through it. Well, because atoms are mostly empty space. They are mostly empty space. Therefore, chance of collision / deflection is small. 7. Explain what is meant by a nuclear chain reaction. 3 marks. Let's write this one out. Let's have a look. Explain what would happen if a nuclear reactor... Okay, explain what is meant by a nuclear chain reaction. You could put when unstable nuclei undergo nuclear fission. We'll put splitting of large nuclei. Further thermal neutrons are released. These thermal neutrons are absorbed by other, most typically uranium. It doesn't have to be. Uranium nuclei and become unstable. Just put, therefore, they decay / split via fission, and therefore we loop background, therefore releasing. Let's write that properly. Releasing further neutrons. Therefore, chain reaction. Good. Explain what would happen in a nuclear reactor if the coolant fluid leaked out of the core. So the coolant is there to cool down the the coolant has a number of things that it's useful for. The coolant takes away the heat from the reactor and transfers it to the electrical generator. So if the fluid leaked out of the core would overheat. Power station would not produce energy. Yeah. The control rods were pushed further into the reaction core. So the control rods limit the number of excess neutrons that come out per fission reaction. And so if control rods are pushed all the way in, then reaction fails to sustain. Reaction fails to sustain. Less power generated, which leads to stopped fission reactions once all the excess neutrons have been used up. Therefore, power station is shut down. If you write, with any of these questions, if you write anything that's similar to this, you will get the marks. This is just my interpretation of it, but these aren't necessarily the completely correct answers. The mark schemes in the real exam and indeed your tests will have a number of correct answers which you could write to get the marks, but if you do write what I've written here, you would get them. Explain what is meant by nuclear fusion. Nuclear fusion is two small nuclei coming together / fusing This is a bit cramped now, but I'm adamant to fit it in, fusing and releasing energy. Explain why two nuclei repel each other when they get close. Nucleus is positively charged. What's going on? Like charges repel. Technically, the closer, there's 3 marks, the closer they get, the more repulsion force they feel. The closer they get, the more electrostatic force experienced. Explain why they need to collide at high speed to fuse together. Well, because they are repelling each other. I'll put electrostatic repulsion increases as distance between them decreases. Large electrostatic repulsion needed to be overcome. Give three reasons why nuclear fusion is difficult to achieve in reactor. So high temperature needed, high pressure needed. Technically, the protons that you're fusing make a plasma which needs to be suspended by a magnetic field. So I'll put plasma needs to be suspended by magnetic field, because if the plasma touches anything, it just melts it, because the plasma the plasma is of order 10 to the 7 degrees, which is very high, and of the order 10 to the 5 Pascal, which is 100 times atmospheric pressure, and so very hot and very, very dense. You don't need to know those figures for GCSE at all. These 2 figures here, you don't need to know them. That's just a little bit of extra information. 3 reasons, and well, yeah, I guess that's it. If you can think of any other reasonable reasons, write in the comments below and I'll see what you think. All right, folks, that is all of these questions completely done. So hopefully you paused the video, you had a go, and then you made your way through these questions as well. If you have any questions, do not hesitate to send me an email or just write in Google Classroom, or even just write in the comment box below, and I'll get back to you straight away. All right, folks, that's me done for today.